features FIR filter that will take some time to make calculation in the DSP. So this feature will had latency in the processing chain of the modules. Instead, in the sub, there are not FIR filters, so the latency of the device is a little bit different. So even here, we are working with different, let's say, time behavior of our sources. And talking about alignment, we are talking about time. Um, Sorry, there is. Then we have a different filtering. Commonly in the subwoofer, there are low pass filter working. Instead, in the clusters, there are high pass filter working. And as soon as I apply filters and equalization in my audio system, I will affect also the phase response of my audio system, because this is physics of sound. As soon as I apply filter and I apply equalization, I will affect also the phase behavior of my system. So all this thing will, let's say, work together to give at each sources its own time behavior. According with this combination of elements, each sources will arrive at our alignment point at a certain moment, and we have to work in order to make this moment equal in the crossover point. So the players, wavelength and period. Just a couple of words about physics. Okay, so the sound waves has a certain length and a certain period. It is really easy to achieve this because the wavelength is the speed of sound divided by the frequency. For example, at 100 hertz, we have 343 meter per second, which is the speed of sound divided by 100. So at 100 frequency, we have a wavelength of 3.43 meters. The period of this wavelength is time divided by the frequency, the same frequency, of course. Time in second or millisecond, so 1000 divided by 100, 1000 millisecond divided by 100 hertz is equal to 10 milliseconds. So a sound wave at 100 hertz has 3.43 meters long and will take 10 milliseconds to travel along this distance. The wavelength in the audio field, the wavelength that we have to work with start at 20 to 20 kilohertz, 20 hertz to 20 kilohertz, with a wavelength of 70 meters to few centimeters. But looking at the crossovers point, more or less, we can talk about frequency that are in between 50 and 100 hertz, 50 and 100 hertz. So with wavelength that start from 3 meter to 7 meter, more or less. This is the frequency we have to work with now and commonly during our alignment process. Another important parameters of our sound wave is which express the sound wave in terms of degrees around the circle. A circle that is the degrees of a circle is 360 degrees. So we can express, let's say, we can define our sound wave in meters, talking about space, in millisecond, talking about time, and in degrees, talking about phase. For example, to define a point in the middle of a wave, sound wave at 100 hertz in the middle. So we have 343 meter at 100 hertz divided by 2, so in the middle, we have 1.72 meters to define the middle of a wavelength at 100 hertz. As well as in millisecond, the period is 10 milliseconds divided by 2, 5 milliseconds is defining the same point, let's say, in the journey of our sound wave, as well as the phase at 180 degrees will define exactly the same point. So we can express according with the calculation that we have to do the same point with three different, let's say, unities. Let's talk about summation of signals, because talking about alignment, it means that we are talking about two signals that must be coherent each other in order to, let's say, guarantee a good summation. As you can see in this slide, we see that when the two waves are in phase, in the bottom part, we have a coherent summation among them. Instead, between them, excuse me, instead, when they are in counter phase, the summation will disappear and we start to have cancellation. Something that that we have absolutely to avoid when we are talking about alignment, because if we will not be careful to the alignment, the risk is to are in a situation of cancellation of the two sources, losing, of course, punch, losing power, losing SPL, losing sound quality. That is not a good thing, of course, talking about audio. So, signal correlation. Talking about two signal, two sound waves at the same frequency, we can see, and same amplitude, we can see that when they are in perfectly aligned in phase, the sum of the two signal result in a plus 6 dB of SPL. As soon as the phase start to change between the two signal, the summation start to decrease. We have less summation. So plus 5.5 with 38 degrees of phase shift, plus 3 dB at with 90 degrees of phase shift, 0 dB at 120 dB of phase shift. So we are losing 6 dB compared to the coherent summation, till a completely counter phase where, let's say, theoretically, we have total cancellation. So we start in a very good situation with a coherent summation, but we could also work in a very bad situation with a big cancellation. So how to detect this, let's say, coherency between the two signals? Let me show you first of all how we have to do measurement in order to detect also the phase value in an audio measurement. You can see a common measurement with just one signal. Commonly, I turn on my pink noise, I send my pink noise to my audio system, I place a microphone in a certain point in my venue, and I see the frequency response of my audio system, the spectrum, okay? But I can see just the frequency response of my system. That is not useful talking about time, because the software measurement is not able to detect the position of the microphone compared to the source, because we don't have a reference signal that says the software where the source is. So in this case, in the second, in the bottom part of this slide, you see that we have a reference signal going in the transducers as well as in the software measurement. In this case, the software measurement is able to detect the difference, to compare the difference between the two signals, the reference signal and the measured signal, and will be able to define the distance between the microphone, the measurement microphone, and the source. In this case, 30 meter. As soon as we achieve this distance, we achieve also the phase of a certain frequency. Because if you remember, the phase is something that is defining a waves along a certain distance, along a certain gap in meters. For example, a wavelength of 3 meters will be duplicated 10 times in this gap, and the phase will rotate 10 times, as well as the period. So how to, this is another slide that shows the single measurement environment, let's say, that is that will be able to give us just the information about the frequency response, and the dual channel measurement that will be able to give us both the same frequency response, but also the phase response and the impulse response, that are information related to the time. How we can set up our audio equipment in order to make this kind of dual channel measurement. Of course, we need an audio card with 2 output and 2 input, and this will be the wiring setup of this is the common wiring setup of an audio measurement system. With in the output, we in both channel we have the same reference signal. Commonly, this is a pink noise signal going to the system, split in the tops as well in the subs. Then in the other output is looped back in the input of the audio card, as well as the microphone signal. So we will have 2 input. One is the reference signal coming directly from the output of the audio card by cables. So without any time shift, because in the cable that there is no, let's say, time shift. Instead, from the microphone to the audio sources, there is space. So the sound will take times to travel along this space, and so the 2 signals will not arrive at the same time. And in this way, the software will be able to detect the time and the phase response of the system where we are trying to align. So, what we can achieve with dual channel measurement? We can achieve the transfer function. That is, let's say, the way to compare the reference signal and the measured signal. This function is called transfer function. With the transfer function, we can know the distance from the source, as well as the frequency response of the source, as well as we can recognize reflection if we are working in environment with reflection indoor or reflecting surface, because a kind of measurement able to detect a time response of a certain system, okay, of a certain source, is also able to detect different sources coming coming in my microphone position. And commonly you can see the reflection in the impulse response, let's say, field, as well as in the phase response field. So to summarize, with transfer function, we'll do audio source alignment, audio sources alignment, subwoofer alignment. So first of all, to make subwoofer alignment, we need to have an audio card with two inputs and two outputs, because we have to perform, let's say, a dual channel measurement and not a single channel measurement. This is the first, let's say, important thing you have to know, and the first important rule. So let's go to make the first, let's say, measurement. Very, very simple. So in this case, our source is the pink noise, and I am sending the pink noise exactly in the same way in the measured signal as well as in the reference signal. Okay, so they are identical. What is the result of this kind of, let's say, measurement? In this case, I am using Rational Acoustic Smart, and but soon we will have our proprietary measurement software inside RDNet. So you will be able to make this kind of measurement also using RDNet. Now the software is in beta testing, and I suppose that in a couple of weeks there will be the first release available in our website for downloading for free after registering. Okay, so let's do this simple first measurement. As you can see, I am sending, using an external DSP, a pink noise in the reference as well as in the measured signal. And the result is a completely flat phase response as well as a completely flat frequency response. This means that at all the frequencies, the two signals are identical. Talking about phase, they are coming exactly in the same moment at all the frequency. And talking about frequency response, talking about magnitude, they have exactly the same SPL at all the frequency we are looking in this moment. But let me do a very interesting example. Sorry, wait a moment. I will. Sorry, there is something that is not working this moment. Okay, let's do this example. I'll try to add a delay at the reference signal, okay? Because the software allow me to do this. So let me add 10 milliseconds of delay at my measurement signal. As you can see, now the phase start rotating, okay? It is really interesting to see that by adding 10 milliseconds, I am adding in my reference signal a period of the wavelength of the waves at 100 hertz. Instead, in fact, you see that the first point in which we are intersecting 0 degrees of phase shift is 100 hertz. Because this means that before arriving here, that frequency will travel for one cycle. for one period. So let me capture this measure and with name 10 millisecond. So now another interesting, let's say, example is by adding 20 millisecond of delay at the reference signal. As you can see, now we have the same intersection point at 100 Hertz, and now the measured signal is arriving 2 cycles before the reference one, because the reference one has 2 cycles of delay at 100 Hertz. This means that we have exactly the same phase behavior at 100 Hertz, but different phase behavior in the surrounded frequencies. But one of the most, let's say, useful things that we can achieve looking at this phase slope, because we have to look at the slope of the phase, is that in this moment the phase slope is going upward, okay, and not downward. Sorry, let me make a quick test with my audio. With my audio processor, which is not on. Anyway, let's skip for a while this test, because my processor in this moment have some problem, and come back for a while in the presentation, because I would like to show you this slide to make let's say to summarize what I said till now. Looking at the slope of the phase trace, we see that if the phase trace is going downward, the measured signal is arriving after the reference one. Instead, if the phase trace is going upward, it means that the measured signal is arrived before the reference one. So looking at the direction of the slope of the phase trace, we will be able to detect, let's say, the position of our sources, okay? So it means that if it is going downward, the source that I am measuring is far away respect at my reference source, commonly the top. Instead, if it is arriving, if the phase trace is going upward, it means that my source is close, let's say, to me. So I have to delay it in order to start to make the alignment. Oh, probably now we are able to make the example that I would like to do before. So come back with our measurement flat at 0 degrees, excuse me, millisecond, and try to apply in this case 10 millisecond at the measured signal. As you can see, now the phase slope is going downward. Compared to the previous example, where the phase slope was going upward, okay? But as you can see, they intersect exactly the same point, because the delay that I am applying is 10 milliseconds, that is one period at 100 Hertz. and this is the 100 Hertz, let's say, position in the spectrum of the phase as well as in the spectrum of the magnitude. If I apply, let's capture this measure and 10 millisecond add and apply 20 millisecond at the measured signal. As you can see, the phase slope of this measurement is intersecting exactly the same point, but it is steeper. This is the most important information, okay? So the greater is the delay of my reference source, the steeper is the phase trace that that I see in the measurement software. This is the first point. So look at the slope of the phase trace in order to have the first information about the position of our sources. The second important things that we have to work with is filtering. So let me apply in this case a filter and remain at 100 hertz in order to avoid to make other calculation. And for example, a Lindquist-Rayleigh filter at the tops in order to simulate, let's say, the behavior of a tops crossovered at 100 hertz. As you can see, with this kind of filter, which is a Lindquist-Rayleigh filter, we have a minus 6 dB of gain of SPL in the crossover point 100 hertz. Instead, with the Butterworth filter, this is minus 3 dB. This is the difference between these two filters. Instead, you can see that with both these filters, we have a complete rotation of phase in the point where we set the crossover. So as soon as we apply a filter at our system, especially a 24 dB per octave filter, the phase will rotate by 180 degrees in that position. So let me capture this, let's say, virtual, because we are still in a virtual situation, but we are going to do also real measurement. Let me capture this trace and call it tops virtual. And then let me create a virtual subs by applying the same filter at the same frequency. As you can see, they are intersecting exactly at minus 6 dB in the crossover point, which is here. But the most important things that you can see is that the phase behavior of the two signals are identical. They have exactly the same frequency response because we are applying the same filter. Lindquist-Rayleigh, 24 dB per octave, 100 Hz. So the equalization will be the same, as well as the phase rotation will be exactly the same. And this, what does it mean? Let me capture this subs virtual. This means that if I now go to unmute the top, you can see that we have a perfect summation in the crossover zone, and the frequency response is coming back perfectly linear, because we don't have any kind of, let's say, cancellation. We don't have any kind of cancellation because the phase behavior of the two signals is exactly the same. So all the let's say frequencies are summing each other currently at plus 6 dB, as we saw in the previous slide. But let me do an interesting example now. Now I will go to delay uh, my tops, for example, by by 10 milliseconds again, uh, simulating to align in the crossover point, let's say, the same frequency, but one cycle, but after one cycle. So I will expect exactly the same summation in the crossover point because I have just shift the tops by one cycle, but the cycle is the same. So I will expect exactly the same, let's say, coherent summation in the crossover point. So let me add 10 milliseconds of delay in my tops, and you can see that there is an interesting, let's say, behavior in this case, because we still have a coherent summation at 100 hertz because we are delaying the signal exactly but by one cycle, but not in the surrounded frequencies, in the surrounding frequency. In the surrounding frequency, we start having cancellation because the phase, as the frequency increase, is rotating more speedily, creating, let's say, uh, differences between reference and measured signal. This will cause cancellation both in the virtual, let's say, domain as we are now, as well as in the real domain as we will be in few minutes. As If I increase, for example, by 3 cycle, by applying 30 milliseconds of delay at my tops, you can see that the cancellation will increase a lot. Okay, so the first, let's say, input that we can see looking at this measurement is that uh, aligning the system using a single tone. Commonly, in some situation, I see some engineer play a single tone at the crossover frequency in order to achieve the maximum SPL level playing with the delay, but just at that frequency. Okay, this is dangerous because, of course, yes, you will be able to align the two signal at that frequency, but you will not be able to detect at at what cycle you are aligning your system. So if you are lucky, you are aligning the system in the same cycle, and you will be in this situation. Okay, if you are aligning in the same cycle. But if you align in different cycle, ripple start arriving in the surrounding frequencies. So something that absolutely we have to avoid in order to let's say to have to achieve the maximum let's say performance from our sound system. So this is another example looking at the slides that what we have just, let's say, do using the measurement software. We aligned, let's say, the same frequency after one cycle. So you can see that at this, let's say, point, the frequencies are still current each other, but just this frequency, not the surrounding frequency that will be not current as well as this. So the work that we have to do is to read the phase trace in order to be sure to be in this situation. So to align our system in the same cycle, both in the tops and in the sub, let's say, um, transducer. Let's go in the real situation. So we are in our venue, and the cluster is still on the ground. And look at the distances that between cluster and front of house and subwoofer or and front of house. In this case, they are equal. Okay, so the difference between these two distances is zero. So the system, from the, let's say, physical point of view, is aligned, but just from the physical point of view. Now we have to deal with the internal latency of the box. We have to deal with the phase behavior of the transducer. We have to deal with the phase behavior of the enclosure of the because of course a big enclosure of a subwoofer will affect the phase differently compared to a small enclosure of a line array modules. But this is not the point also, because when we will go and we will fly the system, the distance between the two sources will not be the same anymore, because now the cluster is far away compared to the previous position. And now there will be 1.6 meter of gap between subs and front of house and tops and front of house. I'm talking about front of house, assuming that the microphone position where we decide to align the system is in the front of house position. We'll talk about that at the end of the webinar, because not always it is convenient to align the system in the front of house position. But let's talk about that after some other example. So what we have to do is apply a delay to this sub in order to achieve the same distance that there is from the microphone position and the top. Of course, if there is the stage, this is not possible because of the stage. So we have to apply a delay at the sub in order to virtual move the sub backward by, in this case, 1.6 meters. So what is the alignment workflow that we are going to do now? So first of all, send the same pink noise both to the tops and the subs. Then mute the subs and unmute the tops. Align the reference signal with the delay finder function of the software, as we will see, and capture the top trace. Then mute the tops and unmute the subs. Capture the sub trace without change the delay finder anymore. Analyze the traces and align the system. Okay, this is what we are going to do now. So let me cancel all this measurement and play with our pink noise to capture the top, let's say, trace. As you can see, no way to achieve nothing. This is the first attempt, let's say, of our measurement. As you can see, there is not a possibility to read frequency response, as well as the phase response is really strange. It is rotating a lot of times it means that the two signals are not aligned. So how can I do to detect the distance between the microphone position and the tops, as well as the time that the sound takes to travel around our DSP, etc., etc. Fortunately, there is an automatic function of all the measurement software that is the delay finder. So playing the pink noise, find the delay, and automatically the software will apply this delay at the reference signal in order to compare the two signals starting exactly at the same point. In that moment, the software will be able to create the graph, the plot of both magnitude and phase response. So let's do it. So turn on the pink noise and find the delay, which is in this case 55 milliseconds, and instantly. Okay. So capture, and let's go to mute. So this is the frequency response of our, let's say, top system, our line array modules, let's say, and this is the phase response of our line array modules. As you can see, the phase in the low frequency is rotating till this point around 200 Hertz, where start working the FIR filter that in the RCF, let's say, line array modules keep the phase more or less flat, starting more or less from 200 Hertz. But we don't care about this because our main work is looking at the phase, let's say, plot graph in this range where we have the crossover point. So let's suppose to have the crossover point at 8 years, okay? And play with the sub and see what happened looking at the phase trace of the sub. So unmute the sub. Oh, look at this. We are really, really, really lucky because in the crossover point, that is this, the phase is the same of the tops and the subs. As you can see, they are intersecting this point that is a minus 120 degrees of phase shift because of the filter, because of the low pass and high pass filter. But they have exactly exactly the same phase shift. So the system is aligned. Perfect. We are really lucky. We don't need to do nothing. Probably is not like this. So let's capture the subtrace and give a proper name, subs, and then unmute the tops in order to see if there is summation or not in the crossover zone. By playing the two signals together, we can see if we have some gaps, as we saw in the previous example with the virtual measurement. So unmute the tops and then capture, let's say, this tentative, this attempt, and we name attempt 1 because we can try to work in order to make a better alignment, as we will see. This is the sum of the tops and the sub in this moment with this setting. So capture and we can, let's say, call this attempt 1. But you can see that here we have a cancellation because just the top had more SPL in this region. But of course, if you see, we have we are lucky in the crossover zone. In fact, as you can see, we have almost 6 dB of summation in this point, but not in the surrounded frequency, because as you can see, the phase trace is absolutely not overlapped each other. They are overlapped just in the crossover point, and we have to work in order to overlap these phase traces as much as possible also in the surrounded frequency. That means that we are trying to find a way to be sure that we are trying to align the system starting from the same cycle. So, do you remember what I said before? When the phase trace is going upward, it means that this sound is coming in advance. Okay, so we need to delay the subs in this case in order to start to keep this phase steep, the steepness of this phase, um, as well as the ones of the top. But of course, we are in phase at 100 hertz, excuse me, at 80 hertz. So how can I do in order to apply the delay without lose, let's say, the coherence in the crossover? Easy. It is enough to add one cycle. So adding one cycle of delay, I will expect that the phase trace will be more steeper. Probably it will go downward, and it will keep the same summation in the crossover zone because I am adding just one cycle. So let's calculate one cycle at this frequency, which is speed of sound divided by the frequency. That is 4 point, let's say 3 meter, 4.3 meter. So by adding 4.3 meter, I'm sure that I will be in phase also in the crossover zone as well as in the surrounded frequencies. So 4.3 meters of delay in the sub. Fantastic. As you can see, now we have almost, let me add a little bit more delay in order to achieve the perfect summation here. We have exactly the same overlap in the crossover zone. And also now, as you can see, let me change the range of our phase. As you can see, also the steepness of the two phase traces is much more, let's say, overlapped. So for sure, this is much better than before. And let me capture the summation between the sum between these two signals. And this is the attempt 2. Let's compare the attempt 1 with the attempt 2. Attempt 1 and attempt 2. Look at the attempt 2. We have a very better summation. Okay, but again, look at the phase trace of the subs in the attempt 2. As you can see, here we have in a good overlap situation, but after, let's say, 80 Hertz, the phase trace is going again upward. It means that we are not aligned still in the same cycle. So how we can do to add more delay, but not by one entire cycle, because probably it will be too much. Let's try to add a half cycle and reverse the polarity. So this is our cycle in meters. If I divide by 2, this is half cycle, 2.1 meter. Okay, so by adding 2.1 meter at my sub and reverse the polarity, that means to reverse, let's say, the way, the direction of the phase, probably I am adding more delay in the sub trace. So I will aspect this, let's say, trace more steeper. And also I will aspect the same, let's say, summation in the crossover zone, because I am adding half cycle with the polarity reversed. So reverse the polarity using RDNet, of course, and add 2.1 meters. We have at 4.5, so we will go to 6.6. Probably a little bit more. Now we are really happy. Look at the two phase traces. They are perfectly overlapped in the crossover zone, okay, as well as in the surrounded frequency. Now we are sure that according with this, with the phase behavior of these sound sources, we are in the in the in the we are aligning the system exactly in the same cycle, because we are in the same cycle in the crossover zone as well as in the same cycle in all the surrounded frequency that are in the crossover area. Let's keep the summation between these two sources, this value, and let's give a proper name and the measurement and call it. So let's compare attempt 1, attempt 2, and attempt 3. As you can see, we have a very important gap between, especially, the first attempt and the last attempt. Because in the crossover zone, especially after the crossover point, we have a gap of 3 dB, which is 2 times the power in that region, because every 3 dB we double the power. So it means that working with the alignment uh, of the first attempt, if we are working with a 1000 watt, we will have just 500 watt in the audience. Okay, so we are losing half of the power of our amplifiers. So it is really, really important to perform, let's say, this kind of work as good as possible in order to overlap the phase traces as much as possible. But now I want to make the last example. If we are very, very, very unlucky and we don't care about measurement, we could be also in this situation. So we could be also in counter phase if we are really unlucky. And look at the measurement in case of totally counter phase. This is a really, really bad situation. This is a really bad situation where we are completely in counter phase between tops and subs. We are losing we are losing something like 9 dB of sound pressure level in most of the crossover frequency range. In this case, we are losing completely the punch of our system as well as the SPL of our system. So it is really, really important to make this kind of measurement. First of all, to be in phase in the crossover zone. And if we are smart guy, we can work also to be in phase, also in the surrounding frequency. That means that we are aligning our system in the same cycle, both with tops and subs. So we are almost arrived, but I want to show you this slide in order to talk about the alignment position. Okay, because if we align in this position, we have a gap of 1.6 meter. Okay, if we align in this position, but if we align in this position, the gap is 4 meter, because the distance now between microphone position and cluster is higher compared to the microphone position and sub. It means that we are aligned here, but not here. So all the works that has been done, let's say, for the alignment in another position is completely lost. So what does it mean? That aligning in one position means misaligning in another one. So what we can do? Where should I place the measurement microphone? Of course, where most listeners are expected, often around the front of house position, close to the front of house position. And most important things, if we are smart guy, in a flat surface, the further away from the sources, the more the space where we have coherency grows. But what does it mean, coherency? So, as we saw, it is impossible to have the same alignment in different position, because as soon as you change the position, change the distance between the sources. Okay, but we can say that if we stay in between plus or minus 60 degrees of phase shift compared to the crossover frequency, we are, let's say, in a zone where the summation will lose maximum 1.5 dB, plus or minus. So the distribution will be 3 dB, that is acceptable for an audience area. So we can say that if we stay in this gap, we are in a real good situation. The greater the accuracy of the alignment in the crossover frequency, looking at the proper cycle, as we saw in the previous example with our measurement, the greater the truth of this rule will be in the surrounded frequencies. So this is really, really, really important to make just a rough alignment, or to make a very fine and proper alignment. Uh, we have we have a good, let's say, we are developing with the help of Michele Begotti and Pietro Mandelli, which are the guys in the engineering support group, this very, very interesting Excel file where we can place our microphone position along a certain audience area. Okay. For example, let's place this microphone at 30 meters far from the stage. And in the data output, I will know the sub delay, the delay that you have to apply to the sub in order to align the system in this position with this crossover zone, with this crossover frequency, and with this position of the tops and subs. Of course, I can increase the level, the height of the tops, and of course will change the the alignment data. Okay. So what can I see looking at this very, very useful uh, uh, Excel file? I can see the green part, which is the 60 degrees corridor, plus or minus. So in this venue, if I align the system with this data, I will be plus 1.5 dB, plus minus 1.5 dB, between 20 more or less and 45 meters. As the distance, if I reduce the distance between the alignment point and the stage, for example, let's go at 50 meter. As you can see, the green part is really, really small. If I go with the alignment point at 50 meter, for example, this green part, the depth of the corridor plus minus 60 degrees is higher. So a very useful Excel file in order to give to achieve let's say this data even without take measurement. Of course, another important things is that if I change the crossover frequency, even this the depth of the green, let's say, um, line will change. As you can see, with a frequency at 100 hertz, the wavelength is um, shorter, and so the place where I am coherent is shorter as well. If I cross over the system at 50 hertz, for example, look at the green line is much bigger. So something that with which we can play in order to decide where align, let's say, our system according with what we expect talking about audience. Okay. And another really important things is this: looking at the documentation that we can that we have in our website, we have these pre-alignment delays that are a document which give us the setting, the delay, and the polarity that we have to apply to RCF active audio speaker in different combination with different presets in order to be sure to start from uh, from this position. Okay, so uh, we are implementing, let's say, in this first value, the internal DSP latency of the boxes, as well as let's say the phase response of the transducer. So just adding the physical distance between the two sources, and probably we will be our system will be aligned. Just looking at this data and also taking measurement of the physical distance between the two sources. This is the document, and you can download this document from our website, and you can see that for all the different combination of system, for example, here we have the HDL 20 in combination with different subwoofer and with all the delay value that we have to apply in order to have, let's say, the same starting point with both the sources. Okay, this is a really long documents because we have most of the combination available with most of the preset available. So, but it is really useful for RCF user in order to be sure to have a good starting point talking about alignment. So, more or less, uh, the 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 messages I wanted to send you has been sent, and now I am available for your questions. And also, I want to remember you that as soon as the virus situation will get better, as it seems in these days, we will restart to make our RCF education program inside our facilities in Italy, where every 3 months, more or less, we schedule a full week of free training about professional audio, let's say, topics, as well as install sound, evacuation, and systems, as well as studio monitor optimizations. So there is video tutorials as well about uh, what we saw today about subwoofer alignments, as well as about RDNet, let's say, software, starting from scratch till the final tuning of an audio system with clusters and sub in different configuration, also with the alignment. So I invite you to see these tutorials in order to to restart as soon as we can to work in the proper way with our show. So hello guys, hello Heli, and I hope that this webinar has been interesting for you, and thank you everyone for your attention. I will
Hello from RCF.
This
In
is
this video,
my
we'll deepen
email. If you want to have the webinar document, I can send you the slides, even if most of the webinars has been done using directly the software. If you need, I can send you an email with with a PDF of the slides that I used in this webinar. And then what can I say? Please write me an email if you have any question. And hello everybody, guys, and thank you again for your attention. I see that most of the question has been answered by Emanuele. So hello Bertrando. Ciao Bertrand. And hello all the guys that are online. See you soon, and let's keep in touch for all.